All right, let's dive into this deep dive you requested, all about quantum physics.
That was good.
We'll be looking at the REE video you sent over.
Okay.
The one called La quantique change-t-elle notre réalité? Which for everyone listening means like, does quantum physics change our reality?
Ah, yeah.
So we'll be exploring those crazy ideas from the video about how particles can be in multiple places at once and how just looking at something might change what it's doing.
Right, exactly. And how it seems like that could even be used to predict things like volcanic eruptions.
Oh, yeah, or even teleport information, like in Star Trek.
Yeah. And I think we should also touch on the race to build a super powerful quantum computer.
Perfect.
It's going to be a fascinating deep dive, that's for sure.
Quantum physics always seems to kind of challenge how we see the world, you know?
It really does. It's like you're peeking behind the scenes of reality and finding this whole set of rules that are governing everything at the tiniest level.
And the video did a really good job of kind of explaining this by like comparing the world we see and experience every day to the microscopic world of quantum mechanics.
Right.
Like they use that example of predicting where an apple will fall.
Okay.
So like with regular physics, we can figure that out pretty easily, right?
Yeah.
But what if we try to apply those same physics rules to like a quantum apple?
Well, that's when things get really interesting and very strange.
Yeah.
Yeah, because in the quantum world, instead of a fixed position, these particles exist in what we call a cloud of probability.
A cloud of probability.
Kind of like flipping a coin
Okay.
until it lands, it has the potential to be either heads or tails, right? So it's kind of like that with particles in the quantum realm. We just don't know for sure where they are until we look.
So it's not that the particle IS in multiple places, it's just that we don't know where it is until we see it.
Exactly, yeah.
So that brings us to those two key concepts the video mentioned.
Okay.
Superposition and indeterminacy, right?
Yes, exactly. Superposition means that a particle can be in multiple states at the same time until you try to measure it. Like that coin we were talking about spinning in the air is both heads and tails at the same time until it lands.
Right, right.
And then you have indeterminacy, which is like a fundamental uncertainty about the particle's properties until they're measured.
Okay.
So even if we know all the information about a particle, we can't perfectly predict both its position and its momentum at the same time.
So it's all probabilities, not certainties, really.
Exactly.
I'm starting to see why quantum physics can be so mind-boggling.
It definitely takes some getting used to.
But honestly, what really gets me is this idea that by observing something, you're actually influencing reality, like the observer effect.
Right.
Remember that analogy the video used? The one with the blank page suddenly having words on it when you look at it?
Yes, I think it's a very powerful analogy.
Yeah.
It really gets to the heart of how observation seems to play, like a crucial role in defining reality.
Like our measurement is forcing the particle to choose a specific state.
Yeah, from all of its possibilities, yeah.
But so if it's observation that's defining the outcome,
Yeah.
does that mean we're like controlling it? Can we like decide what state the particle collapses into?
That's where it gets even more strange, because we don't choose. Even though observation defines the outcome, it doesn't mean that we're controlling it.
Oh, okay.
The particle's choice, you could call it that, it's random. It's kind of like rolling dice. We know it's going to land on one side, but we don't know which one.
So it's like that even with quantum particles.
Yeah, it's very strange.
I bet that caused some arguments among the physicists.
Oh, absolutely. It definitely did. This whole concept of randomness and the role of the observer caused a lot of debate back in the day.
Like with Einstein and Bohr, right?
Yes, exactly.
Yeah.
Einstein really didn't like this whole idea of observer-dependent reality.
Yeah, he believed there had to be an objective reality out there.
That's right. Independent of the observer, like he said, do you really believe the moon isn't there when nobody looks?
That's such a great quote.
It really gets to the heart of the issue.
Yeah.
But even though Einstein had his doubts, all the experiments since then, they keep confirming that the observer effect is real.
Really?
Yeah, no matter how weird it seems.
So we have this strange, uncertain, observer-dependent quantum world.
We do.
But the video doesn't just talk about theory, right?
Right.
It brings up some real-world applications, stuff that's actually happening right now.
It does, yeah.
And I think that's where things get a little bit less out there and more down to earth. You know what I mean?
Absolutely. And I think it really speaks to the power of scientific research.
Yeah.
You start with these crazy ideas,
Yeah.
and then you figure out how to use them to solve real-world problems.
I know.
And one of the most promising areas right now is the development of what we call quantum sensors.
Okay.
They use the sensitivity of quantum phenomena, like superposition, to detect really tiny changes in the environment.
The video even mentioned using them to monitor volcanoes.
It did, yeah.
Like even predict eruptions.
Yeah.
That sounds wild. Can you tell me a little more about that?
Sure. So basically, scientists are using a device called a quantum gravimeter.
Oh.
Quantum gravimeter, it's a very sensitive instrument that can detect really small changes in the Earth's gravitational field.
Wow.
So imagine you're dropping atoms into a column
Okay.
and using lasers to split them into a superposition of states.
Okay.
And then one version of the atom falls slightly faster than the other.
Okay.
And as they fall, they're affected by gravity.
So we've got these atoms falling at different speeds.
Yeah, and they're both in a superposition.
And then what happens?
So you carefully put the split atoms back together, recombine them, and then you look at the resulting interference pattern.
Okay.
And in that pattern, scientists can see tiny variations in gravity.
And these variations could be caused by shifting magma beneath the volcano.
Yep.
So we're using the quantum world to see what's happening under the Earth.
Pretty much, yeah.
That's incredible.
It is.
And I guess we're already starting to see the practical side of quantum mechanics.
Yeah, we are. And what's really interesting is that our understanding of quantum phenomena has actually led to a lot of the technologies that we use every day already.
Oh, right.
Things like lasers and transistors, for example.
Yeah, lasers where all the light particles are aligned in the same energy and direction.
Right, a direct application of quantum mechanics.
And transistors.
Right.
Those tiny things in our computers and smartphones.
Exactly. And those wouldn't exist without us understanding how electrons behave in semiconductors.
Which is all governed by quantum physics.
Exactly.
We take these technologies for granted, but it's pretty amazing when you think about it.
It really is. And now scientists are exploring even more mind-bending applications.
Stuff that, used to be purely theoretical.
Exactly.
Like quantum entanglement.
Yeah.
The video described it as, two particles that are linked.
Even when they're miles apart.
Yeah.
And measuring one instantly affects the other.
That's the basic idea, yeah.
That sounds like straight-up science fiction.
I know. It's definitely one of the stranger aspects of quantum mechanics.
But we'll get into that next time, right?
It will, yeah.
Because I think we both need a minute to process all of this quantum craziness, right?
I think that's a good idea.
We'll be back soon to talk more about those mysteries of entanglement, the possibilities of quantum teleportation, and that whole thing about building a super powerful quantum computer. So stay tuned.
See you soon.
All right, I think I've had enough time to wrap my head around all that for now.
Me too.
But entanglement, that's where I really start to lose it.
Yeah.
I mean, two particles miles apart, somehow instantly affecting each other.
Right.
It just seems impossible. Are we really talking about science here or some kind of, spooky magic trick?
It's definitely one of the most mind-bending ideas in quantum physics, even for people like me who study it all the time.
The video gave that example using two photons, particles of light.
Yeah.
So, imagine you send one photon to, I don't know, let's say London.
Okay.
And the other one stays here in, say, New York.
Okay.
Now, if you measure the photon here in New York and find that it has a specific property, let's say it's vibrating horizontally, you instantly know that the photon in London is going to be vibrating vertically, even though they're thousands of miles apart.
So it's they're connected.
Exactly.
But how?
That's the big question, isn't it?
Yeah, because wouldn't that mean that they're communicating faster than the speed of light?
Right, and that's exactly what bothered Einstein about entanglement.
It did.
Oh yeah, he called it spooky action at a distance because it seemed to go against his theory of relativity, which says that nothing can travel faster than light.
Ah, okay, so that's why it was so spooky.
Right, because it seemed to be breaking the rules.
So I guess scientists had to figure out if there was, a loophole or something?
Right, exactly. For decades, they did all sorts of experiments trying to find out if there were hidden messages or secret variables.
Like some kind of secret code between the particles?
Yeah, or something that would explain how they were connected without actually breaking the laws of physics.
Okay, so did they find anything?
Well, no matter how hard they looked, every experiment kept showing that entanglement is real and there's no cheating going on.
Wow, so Einstein was wrong to be skeptical.
It seems so.
It's like the particles are really connected in some way that we just don't understand.
Right, it just doesn't fit with our everyday experience.
But so, if this is all real and it works, can we actually use it for anything?
That's the next big question, and that's where things get really exciting.
Yeah, because the video mentioned something about quantum teleportation, right?
You did?
So are we going to be beaming ourselves up like in Star Trek anytime soon?
Probably not, no.
Oh, man.
Quantum teleportation is a bit different than how it's shown in science fiction. It's not about transporting matter, it's about transferring information.
Information?
Yeah, like the quantum state of one particle onto another particle, even if they're far apart.
So it's like copying and pasting, but for quantum stuff.
That's a good way to think about it, and it happens instantly.
Still sounds pretty sci-fi to me.
It is pretty amazing, and it could lead to some really cool technologies.
Like what?
Well, imagine a quantum internet where information is sent using entangled particles.
Oh, okay.
That would make it incredibly secure because any attempt to intercept the message would change the state of the entangled particles, and both the sender and the receiver would know that someone was trying to eavesdrop.
So it's like a tamper-proof seal for your data.
Exactly. No more worrying about hackers stealing your credit card information or anything like that.
That would be great.
And maybe even no more spam.
Now you're talking. But the video also talked about something even more crazy. Quantum computers.
Oh yeah, those are amazing too.
But what are they exactly?
Well, the idea was first proposed by physicist Richard Feynman.
Uh-huh.
And he imagined a computer that could harness the power of superposition.
Right, that thing where a particle can be in multiple states at once.
Exactly. So instead of bits, which can be either 0 or 1, you have qubits.
Okay.
And those can be both 0 and 1 at the same time.
So they're like super bits.
Kind of, and that lets them do calculations much faster than regular computers, especially for certain problems.
The video made it sound like they could be super powerful.
They could be, yeah. Adding just a few more qubits could make a computer that can hold more information than all the data in the world right now.
Really? Wow, so why don't we all have quantum computers on our desks already?
Well, there are a few challenges.
Like what?
Well, keeping those qubits in their superposition state is incredibly difficult.
Is it?
Oh yeah, any little disturbance from the environment, like a stray magnetic field or even a vibration, can cause them to lose their quantum properties. It's called decoherence.
So it's really delicate.
Extremely. It's like trying to build a sandcastle on a really windy beach. The smallest thing can mess it all up.
Oh, I see.
But even if we can figure that out, there's still the problem of how to program these quantum computers and then how to get useful information out of them.
So it's not as simple as just turning it on and typing away.
Not quite. It's a whole different way of thinking about programming.
I can imagine.
And then there's the issue of errors. Quantum computers are very prone to making mistakes, and those errors can add up quickly.
So it sounds like we're still a ways off from having quantum computers replace our laptops.
Yeah, for now, it's better to think of them as specialized tools for solving very specific types of problems.
Okay, so like what?
Well, the video gave a few good examples, like materials science. You could use a quantum computer to simulate how molecules and materials behave at the atomic level.
Right, so you could design new materials with all sorts of cool properties.
Exactly, like super strong alloys or highly efficient solar panels, things like that.
That makes sense. What else?
Another big one is drug discovery, using quantum computers to design and test new drugs much faster and more efficiently.
So we're talking about life-saving stuff here.
Potentially, yeah, because you could simulate how molecules interact in a way that's impossible for regular computers.
Wow, I didn't realize the applications were so broad.
Oh yeah, it could even be used for things like logistics.
Logistics, like shipping and stuff.
Yeah, things like finding the most efficient routes for delivery trucks or managing traffic flow in a city. All of that involves analyzing huge amounts of data and finding the best solution. And quantum computers are really good at that kind of problem.
So we're talking about using quantum mechanics to improve everything from the materials we use to the medicines we take to the way we move things around the world.
Exactly.
It's kind of mind-blowing when you think about it.
It is, and it all comes down to these strange rules that govern the universe at the smallest level.
Well, I don't know about you, but my head is spinning a little bit here.
Yeah, it's a lot to take in.
We've covered a lot of ground, from superposition and entanglement to quantum sensors and the potential of quantum computers. So maybe we should take a quick break before we wrap things up.
Sounds good to me.
We'll be back in a bit to finish our quantum journey and leave you with some final food for thought. All right, we're back, and I'm still thinking about all this quantum stuff.
It's definitely a lot to process.
It really makes you realize how much we don't know about how the world works, you know?
Absolutely. Like, we tend to think that everything operates according to the rules we see in our everyday lives.
Yeah.
But quantum mechanics shows us that there's this whole other set of rules governing things at the tiniest level.
Mm-hmm.
And the more we learn about it, the more we realize how much we don't know.
And that ending of the video, it really got me thinking.
Which part?
The part where it asked about future
Oh,
generations.
right. Yeah.
Like, will people who grow up surrounded by quantum technology be able to understand all this stuff more easily than we do?
It's an interesting question, isn't it?
Yeah, like, will it just seem normal to them?
Imagine growing up in a world where quantum computers are just as common as our smartphones are now. Would entanglement and superposition seem any weirder to them than, say, the internet seems to us?
It makes you wonder if maybe we struggle with quantum mechanics just because it's so different from what we're used to.
I think that's a big part of it.
Like, we carry around these little devices in our pockets that can access all the information in the world, talk to people across the planet instantly, even tell us how to get around a new city.
And all that would seem like magic to people just a few generations ago.
Exactly. So maybe in a few generations, quantum mechanics won't seem so strange anymore.
It's definitely possible.
So if we had to sum all this up for someone who's just learning about quantum physics, what would you say are the most important takeaways?
Well, I think the first thing is to just embrace the wonder of it all. You know, it
Yeah.
really challenges our assumptions about how the world works. And it reminds us that the universe is full of surprises and that there's always more to discover.
It's like a humbling experience, but also exciting at the same time.
Exactly.
What else?
I think it's important to remember that quantum mechanics isn't just theoretical. It's already led to some pretty amazing technologies.
Right, like the lasers and transistors we were talking about.
Yeah, and there's potential for even more in the future, like those quantum sensors.
Yeah, or secure communication using entanglement.
And, of course, quantum computers.
It's incredible to think that something that seems so abstract can have such a big impact on our lives.
It really is.
Yep.
And I think that brings us to the final takeaway, which is to just stay curious
Abatka.
about the universe, you know?
Yeah.
There's still so much we don't understand, and it's important to be open to new ideas and to keep asking questions.
Well said. It's been amazing exploring all these ideas with you.
It's been my pleasure.
And on that note, I think we'll leave our listeners with one final thought to ponder. If we have such hard time wrapping our heads around quantum physics now, will future generations even think twice about it? Will quantum mechanics just be like a normal part of their world? It's something to think about, and maybe it'll help us appreciate the incredible strangeness of the quantum world even more. So thanks for joining us for this deep dive into quantum physics.